Thanks everyone who's signed in this evening. Obviously, a massive thank you to Aleks and Sassy for co-hosting tonight. So a few words, just a bit of background. For those of you that don't know me, my name is Barry Cranford. I'm the founder of the London Java community, and I also run RecWorks, which is a tech recruitment company. So here at RecWorks, we try to find ways that recruitment can be a force for good in the tech industry, beyond just getting people jobs. So this all came about 12 or so years ago, when I realized we were spending all day, every day speaking to Java developers and employers of Java developers and Java developers relocating into London. And it was all around this same core group of people. And I started wondering if there was a way that we could use our position within that group to do better things, as a sort of connector between everyone. So over the last 12 years, we've been experimenting with various different ways of bringing people together to that end. So playing with things like making mentor connections, obviously running groups like the London Java community. We've run something like 600 events or something like that, but loads of different experimental things. So the most recent thing we've been playing with is bringing people together on similar learning paths. So we've just started groups around aspiring speakers. And we've put 45 new speakers now up on stage or on Zoom this year, aspiring CTOs and a few other groups in that space. It's all powered by recruitment. So if anyone's interested in looking for work, anyone's interested in hiring, or if anyone's interested in any of the mentoring, anything we do, then come talk to me, look me up on LinkedIn and get in touch afterwards. Love to tell you more. Anyway, on to this evening. So tonight we have the talk on managing state in elastic microservices with Aleks Seović. So Aleks is an architect at Oracle, where he works on Oracle Coherence and contributes to the Helidon microservices framework. Most recently, he led the design and implementation of Helidon GRPC framework, as well as CDI and Eclipse MicroProfile support in Coherence. He currently leads the implementation of Coherence native clients, GraphQL support, and Spring integration. And he is the author of Oracle Coherence 3.5. And he frequently speaks about and evangelizes Coherence at industry conferences and user groups like this evening. So without further ado, Aleks, I'll hand over to yourself.
Thank you. Thanks for the introduction, and thanks everyone for joining. As Barry mentioned, I'm one of the architects on the Coherence team, and today I'll talk about how you can use Coherence to make state management in elastic microservices simpler. As you may be aware, some of you at least may be aware, we have released we have announced two products back in June. One of them was Helidon 2.0, which was a new version of Helidon microservices framework, which provides support for Eclipse MicroProfile. And the other one was the announcement and the new release of Oracle Coherence. We basically open sourced large part of the product and announced community edition. So Coherence has been around for almost 20 years now. I think the first release was back in 2001. So it will be 20-year birthday next year. But this was the first time. It has been available only as a commercial product for those 20 years. And now large chunk of it is available as an open source product. So that's everything I'm talking about today covers that new release. As part of that community, open source Coherence and releasing community edition, we also wanted to implement and showcase the integration between Coherence and Helidon and how combination of the two makes building microservices easier. And in order to do that, we've used the SockShop sample application. This application is not something we have originally written. It was written actually back in 2016 by folks in UK, I believe, nonetheless, from WeWorks. And it was open sourced, and it was kind of intended to be a canonical microservices demo, something similar to what Java Pet Store used to be for Java EE applications back in the late 90s, early 2000s. So the original application is available on GitHub. You can take a look at it. They actually have a live demo that you can run, et cetera, and then they also have the source code for it, which we took and adapted to our needs. So at a high level, just to discuss the architecture, because this is the application, we'll kind of discuss state management in the context of this particular sample application and show you why the way we did it with Helidon and Coherence is simpler than what the original is to some extent, or what some other possible implementations maybe. So the application has a number of microservices. There is a front-end microservice which talks to several back-end services such as cards, orders, users, and product catalog. And then the order service also talks to two more services, to payment processing and shipping service. So it's your typical e-commerce website that allows you to browse product catalog, add things to shopping cart, and place orders, right? So those are kind of the things any application of that type needs. At the implementation level, they wanted to demonstrate a couple of things. They wanted to demonstrate how you can build polyglot microservices. So they use combination of different technologies. There's some are backed by Node, like front end is running on as an Express application on Node.js. Carts, orders, and shipping are implemented in Java using Spring Boot, and then users, catalog, and payment are implemented in Go using one of the Go frameworks, which I forgot which one it is, but same thing, kind of framework. It allows you to build REST APIs in Go. And then, because each of these services pretty much needs a data store, they've also wanted to demonstrate how you can do polyglot persistence. So each service can pick its own data store, and some of them use Mongo, some of them use MySQL. Front end, actually, it's not shown here on the diagram, but front end actually has an option of using Redis for session state management, for HTTP sessions, etc. So that's the original implementation. So let's look at a quick demo to see how that service, what that service actually does. So I believe I'm probably logged out by now. So, oops. So let me just do a quick refresh here. Gonna log in. So basically what this allows you to do is you can browse product catalog. You can search, apply different filters, search for socks. You can add something to cart. You can also view details when you're browsing catalog, et cetera, et cetera. So now that we have something in the shopping cart, we can go there, see what's in the cart. You can update quantity, remove things, et cetera, your normal shopping cart management. And then once you're happy, you can proceed to checkout, and you can see the order has been placed. So I just place it here, and I can also go in and view the order, right? So that's really what the application does. And behind the scenes, as I said, there's those 6 services. Actually, I will show you what's behind scenes. So if you look at this is all deployed. The original application is deployed into our Kubernetes cluster. So if you look at the deployments, you can see that there are multiple deployments here. There is one deployment for cart service, and then there is another one for cards DB, then catalog DB, front end, which doesn't have database, so then orders database, et cetera, et cetera. So you can see that general pattern is that you have single deployment for the service itself, and then you have another deployment for whatever data store is for that particular service. So this is nice from a functional perspective. Obviously, everything works, but there are some problems with this approach, right? I mean, as you could see, how scalable these services really are, right? I mean, once we have this separation, is it enough to scale the services themselves, right? I can easily scale any Spring Boot or Go service or Node.js service that is stateless, but every single one of them pretty much depends on the state that's in some kind of a data store. So how easy it is to scale those data stores? Well, it can be tricky. I mean, those things are not trivial to scale. I mean, you probably have to have different operator for each one of them. You need to configure them in a specific way. You need to use, their clustering support. Some of those features may be commercial, even if the data store itself is open source, et cetera, et cetera. So there is definitely some additional work involved. The second question is, are these services really highly available? And the answer is, unfortunately, they're not. Not until we scale their data stores as well, because the issue is that each of these services is tightly coupled to its data store. So if the data store goes down, the service is effectively unavailable as well. It doesn't matter if you have 1 or 50 or 1,000 pods for a service, for the stateless part of the service. This data store is a fundamental part of the service as well. So if the data store goes down, the service doesn't work. So they're not available, right? And then the last part is, which has nothing to do with scalability and availability, but it is important from operational perspective as well. How easy it is to monitor each of these services. It's possible, it's certainly possible, but there is a lot more to monitor than if the architecture were simpler, because you have these additional components. You have to figure out, you have to learn how to monitor each one of them. You have to configure whatever their Prometheus exporters are. You need to either build or buy or create some monitoring dashboards in Grafana, et cetera, et cetera. So there are many things, or whatever tools you use. There are many things that you need to do in order to be able to monitor them. And then there is another piece. I mean, even if you can monitor metrics, can you monitor what's really happening throughout the system end to end? When the request comes in, can you see what happens all the way down into a data store? Do they all support open tracing? Can you see the spans that started on your application server going all the way down into data store? So all of those things are something that you need to figure out and answer. And the problem is you have to do it over and over again for each different type of data store that you use. You learn Mongo, but that doesn't mean you know how to do the same thing with Redis or with MySQL or with anything else, right? So you have to relearn all these things for all these different technologies and for different platforms again, because how you monitor things on Node will be different, how you monitor things running on JVM, or how you monitor things running, how you monitor Go processes. So there are things to be careful about. And the real problem is that we're really pretending, when we say that it's easy to scale, that everything should be stateless, and because it's easy to scale, we are really pretending that stateful system is stateless, and that's not good, right? We need to understand that we are really dealing with, if we have a stateless service that is tightly coupled with its data store, it's not really stateless, it's stateful, and you need, in order to scale it, you need to be able to scale both the service itself and the data store. So, because there are a couple issues, right? If you only scale service and you have a data store, how far can you scale the service before the load that your scaled out service creates severely impacts performance of your data store? I mean, at some point you may have to scale it just to be able to support additional load, right? And then, as I said earlier, if your data store is down, is your stateless service able to process in-kind requests? More often than not, the answer is no. I mean, it's not. The service itself is effectively unavailable as well. So what we did to improve the situation is we re-implemented all the services except for the front end, because front end really didn't need anything. I mean, we could, but we decided to leave it as is, just so we can show that our services work exactly the same as the original ones functionality-wise. So we re-implemented all backend services using Helidon as a application, as a microservices framework, and using Coherence as a backend. And you can see that in this example, Coherence, which is represented by the red icon in the lower right corner, Coherence is not actually, unlike in this example where we have these data stores as separate things that services depend on. Now we have Coherence internal. We have Coherence embedded into the service itself. From a technical perspective, Coherence is just a Java library, so you can embed it into your Java SE microservices application, just like anything else. Now, it does need to bootstrap itself, or figure out which start a storage server and cluster with other members of the cluster, et cetera, et cetera. And I'll explain in a minute how all of that works. But at the basic technical level, I mean, Coherence is just library that's embedded. It's kind of like using H2 as your in-memory database in your process or for testing or whatever, because it's simply easier to do. Except the difference is you can use it this way in production, because all of these nodes will discover, all the nodes, all the members that you start, all the service pods that you start will find each other. They will form the cluster. They will automatically back up data as far as possible, and make sure the whole system is fault tolerant and can scale out. So that's the architecture. And I'll just go briefly, because I'm not sure how many of you are familiar with either Helidon or Coherence. So I'll go briefly into each one of them, and then we'll see the demo and look at some other interesting things. So Helidon has actually two parts, Helidon SE and Helidon MP. SE is kind of the lightweight microservices framework that allows you to build applications without many dependencies and without having to use any particular technology. It's the lightest way to build services, but it's also somewhat limited because it doesn't have all these other things that we've gotten used to over the years. Things like CDI and JXRS and MicroProfile specs like config and metrics, et cetera, et cetera. So for this particular application, we've used Helidon MicroProfile, which is a full implementation of the MicroProfile 3.2 spec. It also obviously provides support for Jakarta E components that MicroProfile depends on, such as CDI, JSONP, and JSON binding, JXRS, JPA, etc. And it has some features that are really specific to Helidon, and I'm mentioning them here. I want to mention them specifically here because we use them in the application. I will show examples of them a bit later. So one thing that we did in Helidon is we added support for gRPC server, which is kind of similar. It does for gRPC. The goal was to do for gRPC what JXRS did for REST, to make it easier to write gRPC services. And I'll show you in a minute how that works. So that's on Helidon side. And then Coherence, at a high level, you can think of it as simply a distributed, persistent key-value data store. If you've heard of Coherence before, you may have heard that Coherence is distributed cache, and sure, yes, Coherence supports caching, and you can configure different ways to cache, and et cetera, et cetera. But most of our users don't really use Coherence as a cache. They use it as operational data store. And ever since we added persistence, which was 5 or 6 years ago, we see more and more customers using Coherence as basically their system of record for many applications by storing data in Coherence and using it really as a durable, persistent data store. So it is similar in many ways to MongoDB or Redis. I mean, even if you look at the APIs, you can do a lot of the similar things with it, but it is much easier to scale out. And this comes to the architectural differences. Unlike Mongo and Redis, which were designed and implemented as standalone servers, and then later the clustering and multi-server functionality was added to them later. Coherence was designed from the get-go as a clustered system, as a distributed system. So a lot of the decisions that are at the very deep architectural levels have been made to make that easier to do. So you will see in a demo why, how that works, and that truly is the case. It is elastic, scalable, and highly available. It partitions data across cluster members. New cluster members join the cluster automatically, discover and join the cluster automatically, and automatically receive their fair share of data. It ensures that when we have multiple members in a cluster, there will always be a backup. Always. By default, it will ensure there is a backup. You can configure it not to do backups. I mean, if you have data that you don't mind losing and that can easily reload from somewhere else, you can certainly configure that. But in most cases, in vast majority of the real world applications, Coherence will be configured to back up data and be a fault-tolerant, highly available data store. As I said earlier, it is easily embeddable into any Java application. It's just a library, really. And it can also be embedded. I mean, we've done this as part of the demo for the Code 1 open world presentation last year, where we embedded Coherence into Node.js using GraalVM. Obviously, I mean, it's kind of cheating. We're running Node.js application really on top of GraalVM, which is a JVM, so it's easy to run Coherence inside of it as well. But it was kind of cool use case. It is as easy to use for the most part as Java util map. Basic Coherence APIs, such as named map, well, named map in particular extends Java util map. So everything that you know how to do with map, you know how to do with Coherence named map. So you can put objects into the map, you can get objects from it, you can do a lot of other things. Now, there are some extensions that make it more useful for distributed computing. There are ways to send processing into the cluster and do it on a grid side and not on the client. You can listen to events, you can do queries against the map, you can do aggregations against the map, et cetera, et cetera. So there are many distributed computing primitives that are kind of extensions of the map that customers find useful. And as I said, as of June of this year, it's free and open source, and it has quite a few features that you may find interesting, even if you're just using Community Edition. So why Coherence and Helidon together? So it turns out it's a really good fit because Coherence is so easy to embed. We can basically just create Helidon application, Helidon service, and bootstrap Coherence within it. You know, what we did is we created a CDI extension that Helidon discovers or well discovers when Helidon starts it will start its CDI container and it will discover all the extensions, including Coherence extension. And that extension will configure and start Coherence storage server. And as each storage server starts within each JVM, they will, because they're configured the same way, they will form a cluster and you will have Coherence cluster up and running. So in addition to that, to bootstrapping support, the CDI support, we implemented CDI support for Coherence, which allows you to inject Coherence resources such as named maps into Helidon services, which makes it much easier to use from a development perspective. You can also inject CDI managed objects into Coherence using Coherence configuration mechanisms, and then you can finally use CDI observers to handle Coherence server-side and client-side events, which is pretty powerful, and I'll show an example of that a bit later. We did also implement integration with MicroProfile metrics. So all the Coherence metrics, and traditionally Coherence has exposed all of its metrics through various MBeans using JMX. But now we also have the ability to publish those metrics to some external metrics registry. And we've implemented integration with the MicroProfile metrics registry in this particular case. So all the Coherence metrics from the MBeans get published to the same endpoint that Helidon exposes for the application metrics and Helidon metrics, which can then be scraped by Prometheus, and Prometheus can get all the metrics from a single metrics endpoint within the process. We also implemented integration with MicroProfile configuration, which both allows us to configure Coherence using MP config mechanisms, whether it's system properties or environment variables, or some of the MP config files like application YAML in case of Helidon, or MicroProfile config properties for a standard one. So you can use all of those mechanisms and their override features to configure Coherence. And then finally, we didn't really do integration with tracing. Both Helidon and Coherence support tracing. So basically, when you run Coherence inside of Helidon application, the Coherence tracing spans will automatically be included into larger Helidon traces, and I'll show that in a second as well. So let's look at the application as well. So So I will log in here, and I can do all the same things that I did before. So I can search for products, I can add products to cart, look at the cart, place the order, and you can see that I have another order created. So you can look at the order just like we did before. What you'll notice is that there's some minor differences. We decided to shorten the order ID in our new backend implementation. So if you look at it here, you will see that the order ID is much longer. And in the new implementation, the order ID is, something is just in the way. And now the order ID is shorter. So functionally, the application All right, sorry about that. Can you guys hear me again?
Yes.
Okay. Sorry, my internet has been flaky lately. It just goes off on its own a couple times a day. Of course, it happened during the presentation. Okay, so what I was saying earlier, I don't know when I got cut off, but all of the things in the original demo are based on Kubernetes deployments, which are ephemeral by nature. And if any of them goes down, you would lose the data that's in it. So unlike that, I mean, it's good enough for the demo. You can spin them up quickly and do a demo and then shut everything down. Or if it dies, it doesn't really care about it too much. But what we did here is these are all actually backed by, when we look at Coherence deployments, they're all backed by stateful sets. So you can see that for each one of these, there is a stateful set. If I look at the pods, you will see that each pod is named differently. It doesn't have like a GUID-like string that deployments typically append to their pods. It has a numeric, it has a number, 0 in this case, that is appended by the stateful set controller. So each one of these is managed by a stateful set. It has Kubernetes, it has Coherence deployment as a higher level construct, so you can actually see information that's Coherence specific, such as how many replicas are there and which Coherence role and Coherence cluster those deployments belong to. But ultimately, it all comes down to these pods. So if we look at the pods alone, you will notice the difference, right? We don't have, like here we had cards and then cards database, catalog and catalog database. We don't have that anymore. Now, because Coherence is embedded data store effectively, each one of these can both process incoming API requests and manage its own managed state. So we only need one cards pod to have a stateful service now, one catalog pod, one orders pod, et cetera, et cetera. Now, that's stateful service now, but it's still not a highly available stateful service because we only have one, right? And if we go into our monitoring dashboard, we will see that, right? We will see that we have 6 cluster members, which is one for each microservice, orders, payment, shipping, etc. But we will also see that we have 12 endangered services, and each pod basically has 2 Coherence services inside of it, one for actual data storage and one for messaging. So we will see that we have 12 services here. And if we look at services summary, we will clearly see that each of these services is endangered. So this is where the cool stuff really comes in. So what do we need to do to change this from endangered to something that's not endangered? Well, we need to scale them out, right? Once we scale them out, we'll have multiple copies of each, and it should automatically go into a non-endangered state. So let's scale them up. Let's scale each service up to 3 nodes. And again, this is a little bit long command line, but effectively all it does is runs through for loop, and for each service calls kubectl scale Coherence service XYZ to 3 replicas. So once we do that, you should see Kubernetes scaling this out. It may take a minute, but when that happens, you should start seeing changes here. So as these services scale, so we can look at Coherence here. You can see that it's scaling each one of them now. We have 3 replicas, 1 is ready. We can go back here, and in a minute, you should see some of these changing to reflect new members being started. And as you can see, we're going now from, you can see that we went from 1 member to 3 members for these services. And we went from endangered to site safe. And site safe is kind of important to describe as well. Endangered is obviously when we have no backups, and if you lose a particular member, you will basically lose data. It's as simple as that. But there are multiple levels of safety in Coherence. So, because there are multiple ways to deploy it. So the weakest safety level is when you are node safe. That means that you basically have your backup copy of the data in a different JVM, but that JVM is on the same machine as your primary copy. So if you lose physical machine, you could still lose data because you will lose both your primary and the backup copy of the data at the same time. The next level of safety is machine safety, which means that you have multiple machines in the system, and now we will automatically, because Coherence is kind of network topology aware, so it will automatically create backups as far away as possible. So if you have multiple machines in the cluster, we will make sure that you end up in a machine safe state by creating backup on a different physical machine, when we are assigning where backups should go relative to primaries. And then the site safety is kind of the highest level of safety, and it effectively means that your data is in a different site. Your backup is going to be in a different site from a primary data. In this case, it's basically in a different data center. We are using, because this is all deployed in OKE, in Kubernetes, managed Kubernetes service in Oracle Cloud. OKE automatically provisions each Kubernetes cluster across all 3 availability domains in the region. So when we deploy this cluster, we will automatically create Coherence cluster members in each of the availability domains, which are different data centers, and we will create backups in a different availability domain based on Kubernetes zones, effectively, because OKE provides us information about which domain particular Kubernetes node is running in via Kubernetes zone metadata. So that way we can ensure that we are backing up as far away as possible. And what this means in practical terms for you is that you could lose the whole availability domain, whole availability zone, and your data will still be safe. So we got, that's where we got up to 3 nodes. So that's one. So, okay, so we are safe now, but there are still some things to look at. Another thing I mentioned is you want to be able to look at some tracing data and see where the request is coming in and how long it takes to process it all the way down to the backend. So in this case, we have this HTTP request for a catalog service. I kind of pre-canned these traces so we don't have to, we can save some time. But basically, this request came to a catalog service for catalog service size, and it needs to return the number of product catalogs, number of items in the product catalog based on some criteria. So what it ultimately ends up doing is calling getSockCount on our JAX-RS endpoint, which then calls Coherence catalog repository getSockCounts, which then executes Coherence aggregator to determine sock count. So you can see here that we're sending aggregate request to a catalog service on cluster member 2, et cetera, et cetera. And this aggregate request is being processed. You can see that it's count aggregator that we are executing, right? It's executing against socks cache or map. It uses always filter, so we want to get all of them because we don't have any additional criteria. And we are executing it also on member 2, because again, this was done when we had only a single node. If I do that now that we've scaled to 3 nodes, if I go back and well, we've done it. I did a search now. So if I go back and look at a new trace for this same thing, you will see that instead of 11 spans, now I have 17 spans. And that's because now I have 3 aggregation requests happening in parallel, right? So you can see that each one of them goes to a different node, happens in parallel, and then the client gets the result. And you can also see that we are paying cost of cold JVM on the 2 new nodes because those nodes are just executing their first request. But the difference will be, the request is still coming from member 2, which you can see here, but now it's being processed by member 2 and member 12, and member 11. So those are all 3 members that are running catalog service, right? So that just gives you an idea how integrated Coherence is into the tracing mechanisms using via open tracing. And we can look at some other things as well, like the same thing that we did for aggregation, we can do for queries, because we also have the actual catalog API getSocks method, which again calls Coherence catalog repository getSocks, which executes Coherence query. It's very similar to the aggregation, so I'm not going to go into details here. And then finally, we have the most interesting of the bunch, which is the actual order processing, right? Because the order service is kind of the most complex in the whole system. When the new order is posted, and you can see that it's posted via its post request to the well, actually it's here. It's post request to the orders endpoint. It ends up calling order API new order method via JAX-RS, And that then in turn ends up calling user service to get user information, to get the credit card information, to get, I mean, there are multiple, this could obviously be optimized, but this is how the original front end works. So we kind of had to keep it that way. It just calls different things to get the data. So it calls user service multiple times. It calls card service to get the items that we want to buy. And then finally, it goes again into Coherence. It calls this order processor process order, which then saves the order into order repository. And then you can see, so this is all up to this point. This is all Helidon, JAX-RS, your application basically. From this point forward, it is actually a put request into Coherence. So you can see where, and I'll show you something that to demonstrate the difference between running with a single node and with multiple nodes as well. So in this case, we sent put requests from member 3, and because we only had single member, again, that request will also be processed by member 3. And you will notice that there is nothing after that, right? Once we've done the put, there is nothing else to do. But now that we have 3 nodes, I'll add something to cart and submit another order again. And you will see that it's going to be slightly different. Okay, so the order posted. It's there. And if we go back into we'll again see that we have slightly more spans. And the reason for that is that at the very end, now because we have multiple nodes, this put request will not finish here. It will not finish with put process. It will actually have a backup request. So we can see that put request is processed by member 9, and then the backup request is made from member 9, and it's ultimately processed by member 3 coming from member 9, right? So you can see that, you know, now that we are in a fault tolerant, in a highly available mode, we actually once we do put, we also have the backup as part of the execution. So that's all good, but I'll go back to presentation. But before that, I mean, scaling to 3 nodes is, yeah, it's fine. It's sufficient in this case for, you know, to achieve fault tolerance, but it's not, ultimately, it's not anything exciting. Anything can scale to 3 nodes. So when we talk about being able to scale out, we really mean scale out. And again, in this case, I'm somewhat limited. Well, I'm significantly limited by the size of my Kubernetes cluster, but I still can go up to 50 nodes per service. Should be able to. I was able last time. So I'll scale each one of the services to 50 nodes. And this will take a few minutes because obviously Kubernetes needs to start 47 pods for each service and bring the total number of pods to 300, which will pretty much exhaust all the available memory in that Kubernetes cluster. But in the meantime, we can look at some of the implementation details. So they are all scaling out, and you can see that we have 50 replicas requested, 3 are ready, and everything is scaling out. So we'll let that do its thing for a few minutes, and we'll go back to the presentation. So just to summarize, how does Coherence help, right? So what we effectively ended up with are stateful services that are as easy to scale out as the stateless ones. So what I just did with kubectl scale is that's how you would scale your stateless Spring Boot application or your Node.js application. I think that's not how you would typically scale a data store. That's not how you would scale Mongo or Redis or MySQL at all. the high availability is built into the architecture. Once you scale out to more than a single node per service, you have high availability. The level of that high availability may be different, maybe machine safe or not safe, or depending on the infrastructure you're running this on. But ultimately, Coherence will pick up the most reliable, the highest level of availability that it can based on your network topology in the Kubernetes cluster. The support for monitoring is built in. We have all of those Grafana dashboards I showed you. They're all part of Community Edition. They're actually part of the operator. They get installed with the Coherence operator. The operator itself is open source. So you will see that a lot of our competitors, they give you the basic product for free, but then when you need management and when you need Kubernetes support, they basically require that you upgrade to Enterprise Edition and effectively turn into commercial products. We didn't want to go down that path. We had commercial product for 20 years. We wanted to get open source product out that people can actually use, not only for development, but for running production systems and for managing production systems as well. And the bonus of all this, the bonus of Coherence being embedded, the bonus of it being easy to scale is that the implementation can be, and the fact that it uses map as an API, the implementation is significantly simpler. So before I get into implementation, the code for all of this is available on GitHub. So you can go to github.com, Helidon sockshop/sockshop, and that's kind of the main repo. Each service has its own repo. This one is the main repo that kind of has all the Kubernetes deployment scripts and documentation, like the root of the documentation, and explains how you can get everything up and running, either by building it yourself or by using Docker images that we've already built. So feel free to go there and explore and figure out how everything, learn more about how everything works together. But at a high level, let me just discuss a couple things. So one, when you work with Coherence, there is no impedance mismatch, right? There is no object relational mapping of any kind. So in that sense, it's kind of similar to like Mongo and Redis, to any NoSQL data store, right? We just store Java objects. We don't even have, like Mongo has, a document object that things need to be converted to and whatnot, but usually client libraries take care of that for you. So we kind of do the same thing. We have binary objects that we internally store everything in, but it's really just a serialized Java objects. Now, we do support Java serialization, but it's not what most customers, most users typically use, because it's inefficient, it's insecure, it's just not the best choice. Coherence has a highly optimized serialization format that's built in, called portable object format, and it actually, apart from it being much more compact and much faster than Java serialization, it is also portable. It works on multiple platforms. It works in .NET. We have .NET implementation. We have C++ implementation for it. So it can support a number of different platforms. And then we also support JSON serialization, which comes in really handy when you start doing things with clients that only support JSON serialization. For example, our new recently released native JavaScript client only supports JSON serialization. So you can use JSON as a storage mechanism. So that way, if you're building JavaScript application, you can use JSON as a storage mechanism as well. So that way you don't have to do conversion on the server between the formats. But if we need to do conversion, if you have multiple platforms and you're using portable object format as a storage mechanism and you use JSON on the client, we'll do conversion automatically for you. So regardless of which serialization format you choose, it all should work together. The other thing is we support rich domain models. And this is, some of us are really, big proponents of domain-driven design. And, when you do domain-driven design, not having to make your domain objects dumb data classes is very beneficial, because you can actually have logic on your classes that basically mutates internal state of each object by executing a method. So you can encapsulate that domain logic inside of your domain classes, and then you can execute it inside of the cluster. So just to show you the example of that, and it's kind of example of both in-place processing and working with a rich domain model. I mean, this is not a very complex domain logic, but it is domain logic nevertheless. So for example, our cart object has add method that adds item to a cart. And that add method actually has a logic in it to figure out if there is already an item with the same ID in the cart, it shouldn't really add a new one. It should increment the quantity for the particular item. So that's all encapsulated inside the cart class. And what we do from our, this doesn't have annotations, but this is actually a handler, JXRS handler for a post method on the shopping cart service. So when we post item to a cart, it will basically call compute, which is your, again, standard map API. It will call compute on a given cart ID, and it will send this lambda that's highlighted. It will send lambda that does cart add item. It will actually send it to whichever member owns this particular cart, and this lambda will be executed in place. So we don't need to move data over the wire to the application server, to the client in this case, from a data store, and modify it and then push it back into the data store. We're actually just sending a piece of functionality using a Java Lambda, in this case, to be executed wherever that shopping cart lives. And then this item will be added to it, and cart will be updated. Either the quantity for an existing item will be updated, or the item will be added to the cart, and the cart will be stored. So it does make a lot of things significantly simpler once you get used to thinking that, okay, can I send this processing into the cluster instead of, you know, what most of us are used to, moving data from the data store to the client, changing it and sending it back. The other feature I wanted to cover is the event model. So as I said earlier, we did CDI integration, and one of the integrations that we implemented when we added CDI support is the ability to use CDI observers to watch, to listen for coherence events. And coherence internally is very reactive. I mean, it raises events for a number of things, for like restoring data from a disk, to transferring partitions, to in this case entry events on a particular map. So in this case, we want to be notified whenever entry is inserted or updated in the orders map in order to do some additional processing. So you saw in the earlier, in the trace, in a Jaeger trace earlier, you know, the order, when a new order is submitted, it actually gets put into coherence, into this orders map. And it will be put in with a state of created. And this event listener will detect that, and it will take that order and submit it for payment processing. And once the payment is processed, either successfully or unsuccessfully, that order will be updated with the result of the payment processing, which will again trigger the updated event. And if the payment was processed successfully, then the status will be paid, and then we will submit the order for shipping. So it's effectively a state machine that's implemented using the events and the state that the order keeps internally. So it's a very, very nice way to build these applications that, you know, allows you to decouple things and do them asynchronously after the fact. You know, you want to capture the order as quickly as you can, and then you can do all the payment processing and shipping later and handle failure scenarios offline. So that's another example. And then the last example I'll show is the Helidon GRPC implementation. As I mentioned earlier, Helidon is kind of unique among MicroProfile implementations because we did add this JXRS-like GRPC implementation in GRPC framework. So all you need to do is to make something a gRPC service. Yeah, you could still, of course, you could if you want to go down the route of creating protofiles and defining your services that way, you can absolutely do that and deploy service. But we think this is much simpler and should be a preferred way of doing it. All you need to do is create a class that is marked with a gRPC. You can specify a marshaller in this case because we already had REST service for this, and we know that all of our payloads support JSON. We just change marshaller to JSON, so you're not by any means tied to protobuf, which is what you're tied. You can still use it, but you're not tied to it. By default, you will use protobuf, but in this case, we are overriding marshaller to use JSON. And then you can simply annotate the methods that you want to expose with, by specifying which type of a gRPC method they are. And gRPC supports 4 different method types. One is unary, which supports single request, single response. Then you have server streaming, which supports single request, multiple responses streamed to the client. You have client streaming, which is multiple requests and single response once the client is done sending. And then finally, there is bidirectional, which means that client can send request and server can send response across an open channel anytime. So all of those four methods are supported. So you just need to annotate your method correspondingly. So if I changed this, just to give you an example, and then, by default in gRPC, you need to deal with stream observers yourself. So, and you can still do that again, but you don't have to, because if you have unary method, you typically just want to return something. And in this case, we are returning a collection of authorization objects when getAuthorizations method is called for a given order ID. So this will, because it's marked with unary, this will return the whole collection in one shot. And in this case, that's perfectly acceptable. We typically accept only single authorization to exist. We don't expect to be more than a handful, so that's fine. But if we change this annotation to server streaming, then because we're returning collection, or if we return a stream or something, then that will automatically be streamed back to the client instead of being sent in one shot. Another thing that you can do is, instead of returning a value, you can return a completion stage of values, and that will basically turn this service from synchronous into asynchronous. So all you need to do is change, for example, here, this from change the return type of authorized method to completion stage of authorization instead of authorization, and you will turn this into an async method. So that's your server side. Then you simply implement your logic any way you see fit, right? And then, oops. And then on the client side, we kind of did a similar thing to what MicroProfile does for JAX-RS clients. We allow you to define an interface, in this case, payment client. You specify the name of the gRPC service that you want to call, which is the name of this service here. I mean, we could have specified it here, but by default, it will just, it will use the name of the simple name of the class, so we don't have to. So we just say the gRPC name is payment gRPC. The channel is payment, which is either a host name, or you can specify what payment channel maps to. The host imported maps to using MicroProfile configuration. And then we specify the same marshaller that we use on the server. So in this case, JSONB. And then there are a couple things to note as far as the interface goes. We had 2 methods here, but in this case, our client only cares about one of those 2. So it only needs to declare that one. Right, we will create proxy for methods that are defined, not the methods that necessarily exist on the server. Another thing to note is that while the class that is sent as a payload, payment request, is named the same, the other class is not. And in this case, they're basically, none of them are the same class. Payment request is in a different package on the client and in a different package on the server. The authorization is returned from the server, but the client expects payment back. This is completely different class, different package, different class name. All that matters basically is that the payload is compatible. So as long as, in this case, JSON can be deserialized from, the serialized on the server can be deserialized into the payment on the client, and as long as payment requests sent from the client can be deserialized into payment request on the server, it's all good. It will all work. So you're basically tied at a tied by the wire format, not by the actual implementation classes. And then once you have the interface that you need, then you can simply inject gRPC proxy into the service where you need to use it. In this case, we're injecting it into the order service, so you can call the payment client. So that's it on the implementation. Let's go back here and see where we are. So you can see that we are up to 50 members for each service. If we go to main dashboards, you can see that we have 300 members. We've scaled our clusters. Initially, I think it was like 19 gigabytes. We've scaled it all the way to almost a terabyte. So it has significantly more capacity. It has significantly more processing power because, again, each one of these cluster members can go both process your incoming application requests and store the data. So by scaling it out, you're scaling both. You're scaling the processing capacity, you're scaling the throughput, you're scaling the amount of data you can store. So, and if I run aggregation now, we will have a really big trace in Jaeger that shows 300 members running aggregation in parallel. And you can see here that we have 50 replicas, 50 are in ready state, but it's more fun to see the actual pods. So you can see that we have 0 to 49 for users, 0 to 49 for shipping, et cetera, et cetera. So each one of these scaled to 50 pods per service. So that pretty much is the end of the presentation. If you want to learn more about Helidon, these are some useful links that you can go to. Helidon website is at helidon.io. Helidon blog is on Medium, under medium.com Helidon. The project itself is on GitHub, and there is a Slack channel where you can join the team and ask questions, you know, as you go along and start playing with it. And then similarly for Coherence, we have our official website for Coherence Community Edition at coherence.community. Our blog is on medium.com Oracle Coherence. Project is on github.com/Oracle/Coherence. There is a YouTube channel which has quite a bit of content that are, that we did for commercial product, which are still applicable to Community Edition. Some of them may not be, like there's content on Federation and Hot Cache, which are features that are still in commercial edition of the product, but most of it is applicable to all Coherence editions. And then finally, if you want to join us on Slack, you can ask any questions and provide any suggestions you may have there. So thank you for listening and for joining the presentation. If there are any questions, I'm happy to take them. I don't know how much time we have with my disconnect. I guess we are already over time. Anybody still here?
Yes. Great, thank you.
Okay.
For my part. Very interesting. I never thought of the databases as also needing to be scaled up, So very cool topic. Thank you.
Yep, you're welcome. All right. Any questions? So I guess there is a chat. Okay. Because there are no questions on chat. If there are no questions, I guess everybody can go on with their lives. Thank you all for joining. Goodbye.